Welcome and thank you for joining me in this lesson. We have arrived to the end of Unit 1 where we learned about vectors and how to operate with them. And now it's time we use all the knowledge we've acquired to solve some everyday word problems where vectors are involved or applications of vectors. We'll start off with forces as vectors. As we learned in the very first lesson of this unit, forces are vector quantities because they possess both magnitude and direction. The units of force are newtons. Now, imagine that we have two forces, F1 and F2, that apply or are applied onto the same object. Now, notice that forces F1 and F2 are going in the same direction. Their magnitudes are 70 and 90 newtons respectively. If there is an object somewhere, and we apply both forces to these objects, then we are going to say that the two forces applied to the object will produce a resultant force equal in magnitude to F1 plus F2. And the object will move in the direction of the resultant force F1 plus F2. If we want to oppose the motion of this object, we need to apply a third force which must be equal in power, or equal in magnitude we should say, as the resultant force F1 plus F2, but opposite in direction. So this force that will oppose the motion of this object is what we call an equilibrium force. And equilibrium means balance. We're going to call this the force F3. We'll say that the force F3 must be equal to F1 plus F2 in magnitude, but opposite in direction, so minus. Now, this is an example where two forces are aligned, so they are parallel and they even more go in the same direction. But what if two forces make an angle with each other? So let's take a look at what happens then. So suppose that now we have two forces, F1 and F2, that make an angle with each other. So if these two forces are applied on to the same object, then the object will move in the direction of the resultant force. The resultant force here is drawn by using the triangle law and by connecting these vectors head to tail. So this will be the resultant force. So we're going to say that the object located right at this point will move in the direction of the resultant force. In order to oppose the motion of this object, or to keep the object stationary, so in one place, then we will have to apply another force that should oppose the resultant, which means that it must have the same power, the same strength, or better said, the same magnitude as the resultant, and it must go in the opposite direction. This is what we call the equilibrium force. So as you can see, the equilibrium and the resultant force are both of the same length, but opposite in direction. Now, let's take a look at what it's going to look like if we put the forces F1, F2, and the equilibrium force together to form a triangle. Just making some rearrangements here. So if you put the three forces together, F1, F2, and the equilibrium force, that means that the object will not move. We're going to say that the system is in equilibrium. Now, I want us to pay attention or to look at the way that the vectors are connected to each other. So remember that F1 is going this way, F2 is going this way, and F3 has the head pointing this way. So as you can see, the three vectors are all connected to each other, head to tail. When we connect three vectors, in this case that represent forces head to tail, we say that we have formed an equilibrium triangle. Now, knowing how to draw an equilibrium triangle is very important because that's how we can then study the three forces, how they work together, and in the meantime use the knowledge that we have about triangles to solve for each force that is probably required to find, or unknown. So let's take a look at a word problem. Example number 1. We have two forces that act at right angles at some point P. So I will mark the point P right here. Now the force F1 acts north and is 6 newtons. So I will be drawing force F1 acting north this way. I'll point north and I'll call this force F1 equals 6 newtons. Force F2, on the other hand, acts east and is 8 newtons. So what that means is that force F2 is going east and is longer than force F1. We will have to find the resultant of the two forces. And when we're asked the resultant means that we have to find both magnitude and direction. And that goes without saying. So here we go. We are going to create a parallelogram. Actually, it's a little bit more than a parallelogram. It's a rectangle that we're forming here. And we're going to use a parallelogram rule to add these two vectors since they're already placed tail to tail. So the resultant vector will be represented by the diagonal line that connects these two vertices. And we're going to name it R. So we'll say that to find the magnitude of R, we can use the magnitudes of each vector. So we have 1/8 and 1/6 newtons. And we'll say that the magnitude of R squared equals the magnitude of F1 squared plus the magnitude of F2 squared. So F1 equals 6, F2 equals 8. So that will give 100, which makes the resultant R in magnitude equal to square root of 100 or 10 newtons. So this is just the resultant. Now we have to find the direction of it. So to describe the direction, we can either choose to use this angle to find this angle or this angle. So I am going to use the angle theta, the angle made with force F2. So to find F2, obviously we have a lot of options now because we already know all three sides in the triangle, but I am going to use the 10 ratio. The reason why I want to use the 10 ratio is because the 10 ratio will allow me to use the information given. But is it wrong to use the information I just obtained? Definitely not wrong. However, I try to stay away from using the information I've just obtained from solving a problem because you never know if I made a mistake in finding it. So in this way, I can avoid using the wrong calculations in my next steps. Now, we're going to say that angle theta is located opposite to side 6 or vector 6 Newton and adjacent to 8 Newton. So we're going to say that tan theta equals 6 over 8, which makes theta equal to inverse tan 6 over 8. Use a calculator for it to find what angle theta is. We're going to round to nearest degree. So normally you have to round to as many decimal places as specified, and here it's not specified. So inverse tan 6 over 8 equals 36.86. So I will round it to the nearest degree, 37 degrees. So we're going to say that vector R equals 10 newtons. This angle theta here of 37 degrees can be described as going from east towards north 37 degrees in square brackets. Or you can describe the direction of vector R by using this angle here, which would be equal to 53 degrees. So we can say that is from north 53 degrees going towards east. Or we can simply say that it's a bearing of 53 degrees because you're going clockwise from north. Okay, so let's move on to the next example. In the next example, we are given some diagram. We have to find the horizontal force that is required to keep 10 kilogram mass from sliding down a board which is inclined at a 50-degree angle to the horizontal. We know that the force of gravity exerted on 1 kilogram is 9.88 newtons. So let's take another look at the diagram and connect it with the information given. So what we have in here is a ramp, and we have some object that is on the ramp. Practically, we all know that if an object is on an inclined ramp, and in this case we have quite an angle here, an angle of 50 degrees, then the object will fall down due to gravity. So this will represent the gravity vector. Now, we have to find the horizontal force. This would be the horizontal force. So it seems that practically we're able to apply some force in the horizontal direction as indicated to stop the object from sliding down. Now, a little bit of physics knowledge in here. You see another vector that is perpendicular to the ramp. Now, what is this vector about? Remember that one of Newton's law is that when you apply a force onto an object, then it will act against the force. The object will act against that force. We call this the normal force, okay? And it's perpendicular to the ramp. So we're going to name this the force F. We're going to name the horizontal force the force FH. And here is gravity as well. Since we want to create equilibrium, it means that the force is G, gravity, force FH, and the normal force must make a triangle, an equilibrium triangle. So let's create this triangle together. Now remember that all these vectors are not to scale, right? They're just indicating the directions. So what I'm going to do is start off with the gravity vector because that's easiest to draw because it's a vertical. It is represented by a vertical line. And then we have the vector that represents the horizontal force. So that would be the horizontal force right here. Again, keep in mind that we haven't connected the angles, the vectors yet. Now the third force is this one here. And what I am going to do this time, because I want to maintain the same direction, is I'm kind of copying this and I will paste it somewhere. So this will be the direction of the force, and I will make the vector even longer here. So this force is pointing in this direction. So it's important to know how the forces, in what direction they're going. So where the head is pointing at. So now we have to place the vectors. Do not mind the magnitudes, just place the vectors head to tail. So I'm going to play around in here, and I'm going to place this vector here with the head at the tail of gravity. And I will bring this vector here with the head at the tail of the horizontal force. So to make the triangle complete, again, I'm going to extend this. And we also need to make some adjustment to our gravity vector because it was a little bit too long. So now we have the three vectors, which we know that they create an equilibrium triangle, and that's why we stretch them in a way that they create a triangle. So we have the three vectors placed in a triangle. And now we're naming them. So force horizontal, gravity, and then here is the normal force, which we called simply F. Now, in this triangle, we know that gravity will be equal to 10 times 9.8, which equals 98 newtons. So we know the size of the gravity vector, 98. We know that this will be a 90-degree angle. How do we know that? Because gravity is vertical, the horizontal force is horizontal, a vertical and a horizontal line will make a 90-degree angle. So now, In order to solve for any of the other lengths, we're going to need another measurement, because to solve a right angle triangle, we need two things, two measurements, besides the fact that this is 90. So we already have a side length, so we have to search for angles. Now, finding the angle requires a little bit more attention and focus. So what we're going to do is play with this diagram a little bit. So what I'm going to do is extend this gravity vector down here. And as you can see, we have a 90-degree angle. If this angle is 50, that makes this angle down here 40 degrees. Remember that right here we have the vectors F and G placed with each other, tail to tail. So what that means is that if we had the vector G placed in here, and vector F is right here, then this angle made between vectors G and F, placed tail to tail, would be equal to 40 plus 90, or 130 degrees. So right here. So we're going to say that if this angle here is about 130 degrees, how do we know this? Because 40 plus 90, right? That means that this angle here will be whatever is left over from 180. So 180 minus 130. So that will make this angle here 50 degrees. And then we have the last angle here, which would be what's left from 180. So 90 plus 50, 140. And 180 minus 140, 40 degrees. Now that we have all the angles and one of the lengths of the triangle, we can find, or we can solve for any resultant force. And it seems that we need to find both of them, the horizontal and the force, and the normal. So I will start with question A, where I have to find the horizontal, and I will say that the horizontal is related or is located opposite to angle 50, and I'm using gravity, so which is adjacent, so tan ratio. So we'll write down here that the horizontal force, magnitude, divided by gravity, again magnitude of gravity, would equal 1050. That will make the horizontal force Fh in magnitude equal to gravity times 10 of 50. With gravity of 98 newtons times 1050, we'll obtain the magnitude of horizontal force equal to 98 times 50 times 1050 equal to 116.8. So 116.8 newtons for the magnitude of Fh. For the direction of it, we're going to say that it's a horizontal force. So 90-degree angle with force G. And we know this because we know that if we slide over the force, the horizontal force, with the tail placed at the tail of gravity, you can see that the angle is 90. In a similar way, now we'll find the force F. Now remember that force F this time is the hypotenuse. And again, I'm going to use the gravity because I do not want to use a rounded number to find the next unknown. So we have the hypotenuse, we have the gravity that we're using, and I'm going to go this time for the sine ratio. So I'm going to use the angle 40. And gravity is opposite the angle 40. So we're going to say that gravity magnitude divided by force F will be the sine of 40. So that makes